We're going to find the sum of a series, 4 plus 7 plus 10 plus 13, and we're looking for 50 terms. So let's start by writing down what we know. U1 is 4. I can see the common difference there, look, is 3, and it's 50 terms, so n is 50. And I've got a formula that contains all three elements in it. Sn is equal to n over 2, 2u1 plus n minus 1d, as we've just found out. Let's put the numbers in and see what happens. So S50 is going to be 50 over 2 multiplied by 2 times 4 plus 49 times 3. If we work that out, I guess we'll have 25 multiplied by 155. So our final answer is 3875. Not too difficult at all, that one. Let's carry on. Let's look at another one. So here we've got another series to consider. Let's write down what we know. U1 is going to be minus 6. We've got a common difference here, look, of 7. Now, we don't have enough information right now to actually use either of our formulas. We don't have n. So we'll have to do something else. Well, we know the last number is 141. This is a number in the sequence. So why don't we use the sequence formula? Un equals u1 plus n minus 1d to help us. We know the answer to this is 141. That is the nth term. We know u1 is minus 6. And we know that d is 7. So we've set up ourselves an equation. We can use this to work out the number of terms n. So if we just simplify this a little bit, we're going to end up with minus 6 plus 7n minus 7. So if we then add that 13 to both sides, we're going to have 154 equals to 7n. Divide through, and we will have that n is 22. So now I know there are 22 terms in this list, and I can go on and use one of my series formula. I think the one I'm going to use is Sn equals n over 2 u1 plus un, as we've got un, it's 141. Why make it hard for ourselves? Let's pop the numbers in and get this one. So S22 is going to be 22 divided by 2. U1 is minus 6, and we've got UN is 141. So if we work that out, we're going to have 11 multiplied by 135. That is 1,485. There we go. There's our sum. Right, let's carry on and see if we can make this a little more challenging yet again. So, an arithmetic sequence has first term 8. Let's write that down. U1 equals 8. Common difference 2. Okay, great. The sum of the terms of the sequence is 170. So Sn is 170. Find the number of terms in the sequence. So we've got to find n here. Okay, well, we'll do what we can. So let's start off by thinking about one of our formulas. Let's start with Sn equals n over 2, 2u1 plus n minus 1d. Now, we have everything apart from n. We have Sn. So this, if we substitute into this, we're going to create an equation with one unknown. That seems like a good way to go. Let's do it. So 170 is n over 2, and we've got u1 is 8, so we're going to have 16 plus 2 lots of n minus 1, swapping in d for 2. Right, so all we've got to do now really is solve this equation. So we'll times both sides by 2, 340 on the left. That's going to get rid of the divide by 2. And then we will have n, and if we think about this, we're going to have a minus 2 and a 16, so a 2n and a 14. And then if we expand the brackets, divide by 2, and move the 340 across, we'll be left with a quadratic equation, n squared plus 7n minus 170. And is it factorizable? Yes, it is, because we can write it as n plus 17 and n minus 10. So that gives two solutions to the quadratic. Either n is minus 17 or n is 10. But you don't get minus 17 terms in a sequence. It doesn't make any sense for our particular problem. So we're going to reject our negative, and we have our answer. There are 10 terms in the sequence. Okay, now, hard question. What's the hardest thing I could be asked? Well, let's have a look at something really messy and see if we can figure this out. So we have got three numbers, x, y, and z, and they are such that x is bigger than y, which is bigger than, that x is the biggest, then y, then z, and they're all greater than 0. Okay, we're showing something, right? If 1 over x, 1 over y, and 1 over z are consecutive terms in an arithmetic sequence, then x minus z, y, and x minus y plus z could be the length of the sides of a right-angled triangle. Okay, there's a lot going on here. I would suggest pausing the video and having a go at this. What's the first thing you notice? What are your thoughts? Okay, so there's two things that I want to think about. First of all, we can start by considering that the difference is the same between consecutive terms, d, and we can use that to start an equation. The second thing I'm thinking about is Pythagoras, because we're sides of a right angle triangle, so therefore Pythagoras has got to hold. We can put those two pieces together and see what happens. Okay, so let's start with the first thing I've mentioned, right? That common difference. So if I start with the common difference, then that will mean that 1 over y minus 1 over x must be equal to 1 over z minus 1 over y. That has to be true. And if we are thinking about Pythagoras, and we're thinking about the size of those numbers, then another thing must be true as well. Let's write that down too. If I take x minus y plus z all squared, it must be x minus z all squared plus y squared, right? Those two pieces. So what we've got to do maybe is to start with one and get to the other. Right? Okay, we've got to show that that's true. So let's start by considering our original statement with those common differences. Right, okay. So if that's the case, then why don't we try to bring these fractions together and make it look a bit nicer. So that left-hand side we could write with a common denominator and write that as x minus y all over xy. And that right-hand side, y minus z over yz. Okay, now we'll get rid of the fractions completely. Let's multiply and try and make this statement a little bit nicer. So we can put the z on the left, right? So z x minus y equals x y minus z. Okay, so we're just going to times that over there. And the reason I've got rid of the y is because I've cancelled with the denominator. So I've times both sides by yz and it's cancelled with a y, and then I've times the x across. So that statement is going to hold too. Right, from there, let's get rid of those brackets. Zx minus zy equals xy minus xz. Okay, so something like that. And what, remember, we're aiming for is we're trying to get this to happen, right? If we can create that statement there, we have won, right? So how are we going to do that? Well, we could start with that one and work down and then start expanding it, and then trying to match our statements would be a good idea. Let's just put this to one side now then anyway. Let's just move things around. So we'll end up anyway with one side being equal to 0, and we'll say that 2x z minus zy minus xy is equal to 0. Now, I'm going to just stop there and work on the other side of this. And sometimes in exam questions, that's the best way of doing it. I'm not sure still now how to get from there to what I'm aiming for, which is up here. So why don't we start with this one, expand it, and hopefully something will match along the way. So if I'm expanding this, that left-hand side will give us the following result. X squared plus y squared plus z squared will also have a 2xy. Excuse me, we won't. We will have a 2x z minus 2xy and minus 2xy. So that is going to be our left-hand side. Our right-hand side is going to be x squared minus 2xz plus z squared, and then plus that y squared still on the end. Okay, so if we now move those around a little bit, let's collect up some terms and move things around. Maybe we can cancel some things. I mean, the x's and the z's and the y's all squared, they cancel, right? So if we do that, we are going to be left with the following. 2xz minus 2zy minus 2xy is equal to minus 2xz. Okay, now then, we're getting there. Let's just add the 2xz to the other side. And so we'll have 4xz minus 2zy minus 2xy equals 0. And at this point, let's just put a pin in that and see how close our statements are to one another. Pretty close. In fact, we're almost there, aren't we? Because now, if we just divide this all by 2 on both sides, we'll have it, won't we? 2xz minus zy minus xy equals 0. And now they are identical, right? These are the same. And really, we've taken two results and we've proved their equivalence, right? Proof by equivalence, and we are finished, right? There we go. We've shown that if that's true, there are a common difference between them, their consecutive terms, then they equate to something that maintains Pythagoras' theorem.